This video is a three-part series on a seismic retrofit standard used throughout the San Francisco Bay Area called Standard Plan A. Now, the organizations behind me here are the organizations that put it together. That's the Association of Bay Area Governments, Earthquake Engineering Research Institute, Structural Engineers Association, building officials, etc. So it's been well vetted. A lot of people came into the making of it. There's one logo that's not here, and that happens to be Bay Area Retrofit. I was also on the committee and know the entire system that it uses extremely well. Now, I'd like to point out this is a very, very important document. It's been used by the California Earthquake Authority. The city of Berkeley also finances retrofits with this. The city of San Leandro teaches a course to contractors and homeowners. And it's used throughout the Bay Area. City of Hayward actually is starting to require its use. So it came out about 2006, and so it's been almost 14 years that it's been used extensively throughout the San Francisco Bay Area, and literally millions of dollars has been spent, much of it public money. Now, right now, we're going to go over some basics. In order for you to understand Standard Plan A, you need to understand some basic concepts. So we're going to go over what foundation bolts do. We're going to go over what plywood does, and also something called shear transfer ties. Once you have that basic information, then I'm going to compare two houses. And one of them I'm going to use Standard Plan A, and one of them I'm going to use a custom design system, which is what we use. And the Standard Plan A one, you're going to see how it takes almost twice as many retrofit components compared to one that is custom designed like we normally do, and it's based on science. Then for the rest of the video, which is, I don't know, about 25 more minutes, it's pretty long, I'm going to show you the science behind what I'm telling you and why, and I'm going to prove to you that what I'm telling you is true. So let's go ahead and take a look at the basics, and we'll go from there. The purpose of Standard Plan A is to prevent cripple walls from collapsing. I want to show you what a cripple wall is. This is this wall right here. That's the cripple wall. This is the floor that you walk around on, and then this right here is the foundation. Now, what can happen is, as this floor rocks back and forth, this cripple wall can't, withstand that massive amount of weight rocking on top of it. So this is what can happen. So as you can see here, what happened is the floor was rocking back and forth like that in an earthquake, and this cripple wall is starting to collapse. That leaning is the cripple wall actually collapsing to the side. And you can see right here where the house is leaning, and if it were to lean much more, it would certainly fall off of the foundation completely. So the Standard Plan A is doing what it can to prevent that from happening. So this is what can actually happen in an earthquake if you don't have cripple walls that are braced to prevent cripple wall collapse. And this was actually a house that I looked at while I was working for FEMA in the 1989 earthquake. I was assigned to Watsonville, so that's where I saw this house. And I actually went into the house, and it was in terrible condition. The electrical was torn out, the plumbing was shot. Then the main thing I remember most is the plaster. The plaster was just everywhere, the brittle plaster. So what happened was this was torn down. I went by a week or so later, I drove by, and it was a vacant lot. They had just torn the whole thing down and taken it to the dump. So these can sustain enough damage to cause, to lose your entire home, and certainly be a huge inconvenience. So right now we're going to go into the technical parts of Standard Plan A. So remember, this right here is the cripple wall, and we're going to try and keep that from collapsing. Now, this is the cripple wall in its entirety if you were to be underneath the house looking at it. Here's the floor that you walk around on. This is the cripple wall itself, and this is the foundation. And we're worried about this piece of wood right here sliding on top of the foundation, and we fix that with bolts. The other thing we're worried about this piece of wood called a floor joist sliding on top of this piece of wood, which is called a top plate. Now let's go ahead and see how that's done. So if you come over here, you'll see that here's the cripple wall. It's just, standing there like it's supposed to. Then the earthquake force comes this way, and it tries to knock it over like that. And it's a pretty easy solution. All you need to do is put some plywood on the cripple wall, and that solves that problem. Now the next one we have here is the bolts. So this is the mud sill. It's just sitting right here, as you see it right here. So remember, that's the bottom of the cripple wall. Earthquake force comes this way, tries to push it off like this, and then we simply bolt it to the foundation. Now on the top, we have the same problem with sliding. So here's the floor you walk around on. This right here is the floor joist. And we want to make sure that when the earthquake force tries to push against it, it can't move. You see how those dotted lines show how it's moved, moved a foot or so. We want to make sure it doesn't move. And so we use these are called shear transfer ties. And you can see right here, that's a piece of metal here and a piece of metal here and a piece of metal that will keep that from sliding when an earthquake hits. So in summary, we're going to keep the cripple wall itself from collapsing by putting on plywood. We just nail some plywood to it. The next thing is we're going to keep our cripple wall on top of the foundation by bolting this piece of wood called a mud sill to the foundation. We do that right here with the bolts. And finally, we're going to keep the floor that we're worried about moving onto the top of the cripple wall by putting pieces of steel right here, connecting this piece of wood to this piece of wood, as shown right here with the shear transfer ties. Now, standard plan A, what it does, it gives a system by which we can take any house and figure out precisely how many linear feet of plywood we need, how many bolts, and how many shear transfer ties. And we're going to go ahead and look at that part right now. And this is the technical part, and this is the part where you're going to see a lot of problems. When talking about earthquake forces, we refer to pounds of force. So let me explain how that works. What actually happens in an earthquake is the ground moves underneath the house like that. So the foundation and everything just goes like that. And then inertia wants to pull the house back like that and cause it to slide from its foundation. Now that is exactly the same as something pushing on the house. So let's assume that you have something that weighs, let's say it weighs 10,000 pounds and it's pushing against the house, like this. That is the same as a ground acceleration measured in G's underneath the house. So we're actually looking at a ground acceleration under the house, and we're translating that into pounds of force that are attacking the house. So what it is, when we're looking at hardware and we look at anything else, we look at them in terms of pounds of resistance. So you're going to see references to different types of hardware, to houses being attacked by a certain amount of force, and that's what it means. In the world of seismic retrofitting, we're always talking about pounds of force that are pushing against a house and the pounds of resistance to make sure a house does not fall off its foundation. So let me show you how that works. So right here we have a ground acceleration that goes underneath the house. The ground moves under the house, and you see how the house was originally upright. You can see that with those dotted lines. So it was originally upright, and now the house is trying to move underneath it. And inertia is causing the house to lean, and is also going to want to cause it to slide off the foundation right here. And that, of course, that's what a retrofit is to prevent. Now look, this is the exact same thing as if an earthquake force were pushing against the house. So you see how it is upright here, and then it gets pushed on, and then it's going to lean like that. So now this image and this image are identical, except one is caused by earthquake force moving underneath, one is caused by earthquake force pushing. Now that pushing force is rated in pounds of force. So all hardware is designed to resist a certain number of pounds of force. That has to do with plywood, bolts, any type of hardware at all. So what we do in every single retrofit is we figure out what the pounds of force will be, and then we figure out what type of hardware we'll need to install to resist that same number of pounds of force. So basically it works like this. This force right here, this ground acceleration, we translate that into a pounds of force that are pushing on the house, and then we take that number and then we come up with the hardware we need. So right now I'm going to do a comparison between using standard plan A and using a science-based retrofit on the same house. This is a 1,500 square foot house that is with stucco siding. So the first thing we see is that this house, it must resist 8,280 pounds of earthquake force in all directions. And if we use standard plan A, we discover we're going to need 45 feet 4 inches of plywood on each side. So we have that much here, we have that much plywood here, we have that much plywood here, and we have that much plywood here. Whereas if it's based on science, we only need 10 feet on this side, 10 feet on this side, 10 feet on this side, 10 feet on this side. Now, the big difference here is just the way the plywood's put up. The one standard plan A, it's put up in a not very efficient way, and the one on the right is extremely efficient, and that's why the big difference in the amount of plywood. Now here we have the shear transfer ties. Standard plan A, we're going to need 15. Based on science is only 10. Again, this is all on each side of the house. Remember, we have to put the same amount on each side. So same amount here, same amount here, and same amount here, and same amount here. So the reason for that is that standard plan A, when they determined the ability for shear transfer ties to raise earthquake force, they undervalued it. And that's in the manufacturer's catalog. It's 100% verifiable. That's just the way they did it. And the exact same thing about the bolts. So as you can see, we're going to need 12 bolts using standard plan A on each side, and based on science, we're only going to need 8. And so the amazing thing is, when we're all done, look at the difference in the total quantities. For standard plan A, we're going to need 180 linear feet of plywood, 60 shear transfer ties, and 44 bolts. Whereas if we use retrofit based on science, we're going to need 40 linear feet of plywood, 40 shear transfer ties, and 32 bolts. So the rest of this video is going to be to prove to you why it is that the plywood is so weak the way standard plan A does it. After that, in part 2, I'm going to show you how plywood should be installed so that it's very efficient, very strong, and you don't need nearly as much. And then I will also be showing you into part 2, and then also into part 3, I will show you what the problems are with the bolts and the shear transfer ties, and why it is that standard plan A has these quantities that are far more than they need to be. So ultimately, standard plan A is extremely inefficient and extremely extremely expensive to resist the same amount of force as a retrofit that's based on science. So every standard plan A retrofit is based on this table, so we're going to go ahead and make sure that you understand how to read it. So the first thing we look at in any standard plan A retrofit is the square footage of the house. So assume your house is 1,200 square feet. We'd come down here over 1,200 square feet, and then we figure out, is it made out of stucco on the outside or is it wood? If it's stucco, it's called heavy construction. If it's wood, it's called light construction. So we come down here, we have 1,200 square feet. It's stucco, therefore it's called heavy. Now we go over to the plywood column. So here we have the plywood. We come down here for our house, and we end up with 20 linear feet of plywood needed. And then we come up here with the bolts, exact same thing. We come over here at the UFP 10, we go down the column and we see 6. If we were to use 1/2 inch bolts, we'd come down here and we'd see 9. If we'd use 5/8 bolts, we'd come down here and we would use 7. Now the exact same thing with the shear transfer ties. And, these columns right here, we have an L70. It's a type of shear transfer tie, and we're going to need 17 of those. If we use an H10, that's a type of shear transfer tie, we're going to need 13. And for an L90, we're also going to need 13. Now, I'd like to point out the L90 and the L70 are pretty much the exact same piece of hardware. It's just that the L90 takes a few more nails. So this table is where all the problems with standard plan A start, and that's because standard plan A assumes that the plywood and the bolts and the shear transfer ties can resist a certain amount of force, and it's simply inaccurate. From here on, we're going to be looking at the science, what the manufacturers say the certain hardware is going to resist, what tests have shown, and also what the building code tells us. And these values are different from what standard plan A tells us. The table on the left is found in standard plan A, and it tells us the connector capacity, in other words, the capacity of all these pieces of hardware that are in that table. And for example, for the L70 right here, it tells us that it can resist 458 pounds of earthquake force. For the L90, it's 600 pounds of earthquake force. Now let's go ahead and see if that's accurate. So here's our L70. We come over here and we look in the manufacturer's catalog and the test report, and it says it can resist 740, which is quite a bit different than the 458. Now the same thing with the L90. It's telling us here it's 600 pounds per piece of hardware, and right here we have 925. So let's go ahead and see what it says about the other hardware. So now we're looking at the H10 hardware. That's one of the hardwares that was in that table we looked at. And what it says here is it can resist 505 pounds. Now, in actuality, in the manufacturer's catalog, there is no such thing as an H10. So we're going to assume they meant either the H10A or the H10AR as if they're the same. However, if you look at the actual table, the H10AR is 490 pounds, which is different than the 505, and that the H10A is 590 pounds, quite a bit different than the 505. So this is another inaccuracy in the table. So let's take a look and see how they did with the bolt. Standard Plan A says a 1/2-inch bolt can resist 820 pounds, whereas the actual calculations shows it can resist 1,119 pounds. The same with the 5/8 bolt. It says it can resist 1,170 pounds according to Standard Plan A, and actual calculations so it can resist 1,555 pounds. So you can see the problem here. If it can actually resist 1,555 pounds, that means your bolts are actually a lot stronger than what Standard Plan A says. So if you put in the bolts that Standard Plan A says to put in, you're going to end up putting in too many bolts. Because it's just not accurate. It's just, we're not in touch with reality here. So Standard Plan A did actually get it right on one piece of hardware, and we're going to look at that one right now. That happens to be the UFP10. This is a UFP10 right here in this image, and what it is this is a piece of hardware that bolts to the side of the mud sill. So you have these bolts right here, and then it bolts into the concrete. And that's done when we don't have any room to put in a regular bolt. Here's an actual photograph of what I'm talking about. So here's the UFP10. Naturally, we couldn't put a bolt coming down in here because this is only like 8 inches between here, and you can't get a drill motor in. So this is what they look like. Now, this 1,340 pounds, that is only if it's in Douglas fir. So this right here looks like a piece of pressure-treated Douglas fir, which we see in houses that are built from 1973 on. But these houses that we're retrofitting are usually built before 1973, and they're all made out of redwood. And when they're made out of redwood, we must multiply it times 0.74. So we take that value, the 1,340 pound value that we had in Douglas fir, we multiply that times 0.74. And then we end up with a value of only 991 pounds when in redwood, which is what 99% of the old houses have. Basically, every single piece of hardware, every bolt, every framing anchor, everything that they put into that table, they got it wrong. And they got a lot more wrong, and we're going to see what that is right now. So let's see what this table should look like if we were to apply it to Douglas fir, which is one type of wood that we see, and to redwood. The first thing, the L70, we would see that its actual value is 740 pounds of earthquake resistance per piece of hardware. For the L90, it should be 925 pounds. For the H10, and again, there is no such thing as an H10. It's either an H10A or an H10AR. They have different values. One of the values is 490 pounds, and the value for the H10A is 590 pounds. So then we have a 1/2-inch bolt. That should actually be 1,119, and then for the 5/8 bolt it should be 1,555, and the UFP10 is accurate. UFP10 is 1,340 pounds, so that they did get right in Douglas fir. Now, as I stated earlier, a lot of the work we do goes into the redwood because that's a lot of the older houses we made out of that. So on the right-hand side, let's see what the value should be when redwood is part of the retrofit. So the L70 provides 437 pounds of earthquake resistance. The L90 at 684 pounds of earthquake resistance. the H10, either the H10AR at 362 or the H10A at 436 pounds. The half-inch bolt, 828 pounds. The 5/8 bolt, 1,159 pounds of earthquake resistance. And the UFP10 at 991 pounds of earthquake resistance. So anyway, it's just good to remember that when you're thinking about doing a standard plan A retrofit, that these values that it's based on are inaccurate, and you should think about at least finding out accurate values. And you could actually create a table if you wanted to. I can't see why you would, but if you're going to have a table, at least have accurate values, and then you can do it whatever you want with it. So anyway, I just thought anyone who's going to use standard plan A should be aware of this. As we saw earlier, this is the reinforcement schedule that's the basis of standard plan A. Anything you do or any house that you retrofit with standard plan A must refer back to this table. And as we saw, most of the values, in fact, all of the values for the hardware are wrong. And the one value we didn't look at yet was the plywood bracing, and we're going to go ahead and see how they did on that one right now. When we're looking at the plywood, the first thing we notice is where it says Cripple Walls to be braced with 15/32 rated plywood with 8D nails at 4 inches on center. What that means is that the plywood will be 15/32. The grade is rated. And why we decided to use rated and not structural one, I have no idea. Structural one is actually meant for shear walls. Rated is not. It's just a plywood, has earthquake resisting, but it's not actually meant for shear walls like structural one is. And then it says with 8D nails, that's a certain size nails, and 4 inches apart on edges. So basically it's a piece of plywood, you put nails every 4 inches on the edges. They happen to be 8-penny nails, and that's pretty much how they want the plywood done. Now, we were restricted at that time in terms of how many nails we could put in. The strength of a piece of plywood is dependent on the spacing of the nails. So, for example, if you have a piece of plywood and you nail it 2 inches apart on the edges, you'll end up with this value right here of 870 pounds per linear foot. If you nail it and if you use rated sheathing, which is what we have right here, and you're going 4 inches apart, we end up with 380 pounds per linear foot. And that's actually what the committee decided to use. We were actually restricted by another part of the building code, but we went ahead and went with the 380. Now let me show you why we couldn't go higher values for our shear walls. At that time, and it's no longer part of the building code, it said that in seismic zones 3 and 4, and we're in 4, where allowable shear values exceed 350 pounds per foot, that means if we were trying to make shear walls that are stronger than 350 pounds per square foot with our plywood nailing, foundation sill plate shall not be less than a single 3-inch nominal member. That means all their mud sills, which are currently 1.5 or 2 inch, would have to be replaced with 2.5 inch thick mud sills, and we're not about to do that. So instead, they put 1.5 inch blocking on the mud sills, and we just did twice as much linear footage than we would normally have to. So rather than being able to use the 870 pounds per linear foot plywood nailing, we were restricted to the 380, and the retrofits ended up being a lot more expensive. As I said earlier, the nailing restriction has been lifted. That's no longer part of the building code. And if we were going to do it now, we could use the 870 pound value. We could put in half the linear footage of plywood, which means half of the labor, a huge reduction in expense if we would simply follow what the building code says we could do right now. So anyway, that's some of the problems with the plywood, and we'll look at some other problems it has right now. So we just looked at the plywood nailing for standard plan A, and it was at 380 pounds per linear foot. And just to be clear again what that means, remember the bolts can resist a certain amount of force per bolt. The L90 can resist a certain amount in pounds per piece of hardware, and the plywood can resist a certain number of pounds per linear foot. So in this case, we're saying 380 pounds per linear foot. In other words, if an earthquake were to push on it with 380 pounds of earthquake force, it would fail if it were nailed 4 inches on center, like standard plan A says. However, standard plan A made a big screw up. and the way they require the nailing. We'll take a look and see what that is. So here is the floor. That's the floor framing we're trying to keep from sliding on top of the shear wall, the cripple wall. So this is going to want to slide like this. So what we do is we put this framing anchor here. This is an L90. So what we've done is we nailed it here and we've nailed it here. So then when it tries to move like this, it transfers the force into that upper top plate. That's this 2x4 right here at the top. Remember, there's a bottom one and there's an upper one. So it transfers that movement into this upper top plate, and then that goes into the nails. So here's a nail here and a nail here and a nail here. These are the nails at the top of the plywood. And when that happens, it goes from the top of the plywood to the bottom of the plywood where all the bolts are. So that's how the whole thing, that's the whole load path. That's what we're trying to do. Now, if you look over here on this side, you'll see that these nails are actually 4 inches apart, staggered, meaning there's one here that's 4 inches, one here that's 4 inches, one here that's 4 inches, one here that's 4 inches. In other words, the difference between this one and this one is 8 inches. Between this one and this one is 8 inches. This one and this one is 8 inches. Now all the force is going into the nails in the upper top plate, and let me show you why. This L90 right here, it's nailed into this joist right here, which is what it's supposed to be, and the nails are 1.5 inches long. And then there's the nails that come down this way, and they're also 1.5 inches long. So the nails are only pushing on the upper top plate. And so all the force is going into the upper top plate, all the sliding force. Therefore, all that sliding force is going only into the nails at the top. So it's only a nail that's every 8 inches rather than every 4 inches. So that means that the standard plan A shear walls, the plywood strength, if you followed what the standard plan A says, is only 190 pounds rather than 380 pounds. And that just really gets ridiculous. I mean, we could have used 870, now we're down to 190. And in order to meet the anticipated ground acceleration for practically any house, you had to put in so much plywood like this, it would just be absolutely ridiculous. One of the big problems with the plywood is knowing how to attach it to the bolts. Obviously, the plywood isn't attached to the bolts. It can't do anything. Let's go ahead and look at this drawing and see how the whole thing would work. So this is the cripple wall. That's what we're trying to prevent from tipping over. And the piece of plywood is what actually prevents that from happening. However, it has to be attached to the bolts. And if you put in the bolts, right here there's a bolt, and right here, here's a bolt, but you don't attach it to the mud sill somehow, it's just going to sit right on top of the mud sill and there won't be any connection. So here you can see it right here. Here's a bolt right here, but the plywood is just sitting on the edge. So if this plywood were to rock back and forth, it would just slide right on top of the plywood right here, which would mean it's not going into the bolts and it's not connected. It's basically just a piece of plywood flopping around on the wall. So we need to make that connection. And Standard Plan A has a particular way of doing it, and I'm going to show you what that way is. So let's take a look at the problem once more. As you can see, the plywood right here is just sitting on top of the mud sill. This happens because the mud sills are usually 6 inches wide like this, and then the studs of the cripple wall are only 2 inches. So when you put the piece of plywood on there and you nail it to the studs, it's just sitting right on top of the sill and it's not attached to the bolts. So the way Standard Plan A fixes that is they put blocks in between the 2x4 studs. So here's a block here, a block here, a block here, and then they'll put the bolts through the block. So here's a bolt that comes down this way, another bolt that comes down this way. And the solution at that point is real simple. You just take your piece of plywood and you nail it here, and you nail it here, and you nail it here, and you nail it here. So you've nailed it into the blocks, which are in turn attached to the bolts. And so this is achieved exactly what we wanted to achieve. And this is the way that Standard Plan A does it. It's not the best way. There are some other methods that are better that were evaluated while I was on the Standard Plan A committee, and I'll be showing those to you right now. So here's a photograph of somebody putting in the blocks. There's the 2x4 block. Here's the mud sill. That's, you can see how it's wider. It's probably 6 inches. This is 2x4. And then these are 2x4. And then we put the plywood on. It will be nailed into these blocks here at the bottom. The problem with this method is the blocks can split. So you can see right here, there's a split. Here's another split. Here's another block right here where it's split because of this nail right here. And actually, it's fairly common. I used to, when I was first starting out a long time ago, I used to split a lot of blocks when I'm, putting the blocks, and they just split. And the tendency is for a contractor just to leave it there. I mean, they are not fun to take out, I guarantee you. So, I take them and I'd have to pull them out, split them, pull them out, split them, pull them out. And I find that, man, there's got to be another way to do this. And I did figure out some other methods, and I'll show you what those are right now. One of those solutions is to cut the mud sill flush with the 2x4s. So you can see how we took a saw and we cut it flush with the 2x4s. And then we simply put our piece of plywood on here and we nailed it here and on the sides and at the top. And, we like this because it's a direct connection to the sill and to the bolt. So there's a bolt right here, and then there's a bolt behind that hole right there. And so anyway, this is a really good method. It's actually considered to be the best method, as we'll see shortly. One of the really nice things about this method is that you are nailing into old growth redwood. So you can see this wood right here, see the close growth rings, very tight, really hard to split, really hard to pull the nails out. And right here, this is what you get at a lumber yard from a tree farm. So when you do the flesh cut method, you end up with high growth, really high strength wood in the mud sill, and all the rest of it is old growth. So you can get a really good strong shear wall with the flesh cut method. Another method is to use staples instead of nails. As you can see, this block right here, there's a bunch of staples in here. There's probably the equivalent of 30 nails. So this is a very, very strong connection with no issue with splitting. And if we ever have to use blocks, that's what we always use. So here we come to the last method. This is called the reverse block method. It's pretty simple. This can only be done if this mud sill right here is pretty wide, say 8 to, probably 8 inches is what you're looking for. So what we do is we have our piece of plywood right here, and then we have this 2x4 that we put, next to it right here, and then we nail it from the back. So it's, nailed, 2 inches apart or whatever. Then we take this whole assembly and then we put it right here on the mud sill, and then we nail it down here into the mud sill itself where the bolts are. And then we nail it here, and we nail it on the top, and then we nail it down this way. So that is the last method. This is actually, there's only 4 methods to do this, and this is, you've seen all 4. When I was on the committee, I had these methods evaluated by the largest research laboratory in the world regarding shear walls. Their tests are the basis of the building codes in Canada as well as the United States, so their opinion is a big deal. The letters you can see was written to me directly because I'm the one who wrote them the inquiry letter asking for the evaluation. So you can see this is way back in 2003. So this, the standard plan A is getting pretty old now. And the different methods were rated from most preferred to least preferred. And as you can see, the flesh cut method is the most preferred, primarily because, as we saw, it can't split the block. You can go straight into the mud sill. It's old growth wood. It's got, no materials that have to be used. I mean, it's, it's green. It's got every good thing about it. Whereas he said that the nailed blocking method is, has a lot to be desired. One of the reasons being that it's, really not a tested system. The flesh cut method, you have 2x4s on the bottom, 2x4s on the top side, just like a normal test would have. And normal tests done by these research laboratories do not use blocks. So now that you've looked at standard plan A and you've seen how, the plywood is just nailed in a very inefficient way, that they did not read the catalog values correctly for the hardware and the bolts, you can see exactly how this happened. And it would be pretty easy to fix. It just needs, the committee needs to meet again, get the proper values, nail the plywood correctly, and it could actually be a really simple fix. But for right now, if you follow standard plan A, this is what you end up with. The last thing I'd like to point out about standard plan A is where it says provide new mud sill bolts or anchors outside of braced panels at 6 feet on center or less. That means they want to bolt every 6 feet all the way around. And the reason that's a problem is that you end up putting in a bunch of bolts that don't do anything. It's an engineering principle, engineering 101, that only the bolts that are attached to the plywood do anything. And this has to do with the fact that all the earthquake force goes into the plywood. It's like a shock absorber, and all that force goes into the bolts where the plywood is, and you should put a bolt in every 2 feet wherever the plywood is and not do anything else. So this ends up being a whole bunch of extra bolts that you don't need. So this is a case in point of what I mean. Here you have the mud sill that is sitting right on top of the foundation, which is right here. It didn't slide off. And this is a big earthquake. I mean, it's, the house slid right off, but look, this was actually a really small cripple wall. You see, that's actually the stud that used to be upright. This is a really small cripple wall. It slid. This stayed right where it's supposed to be, and that's because of all the nails that are in it. Remember the nails? There's a big nail about every 32 inches or so along this whole thing, and that's why they don't slide off. And that's why it's a total waste of time to put bolts anywhere where there's no plywood. I can see why putting it where the plywood would make sense, because there's a lot of force that goes into the plywood, into the mud sill. But doing it outside the plywood panels, it just doesn't make any sense. Conceptually, I think Standard Plan A was a really good idea, the way it's laid out. Jim Russell, who was he was the chair of the committee that put the original retrofit building code guideline in Appendix Chapter A3 of the California Existing Building Code. He was the chair of this committee, but then, as I may have mentioned earlier, he got really sick, and after just a couple of meetings, he had to drop out. So what happened was it was put into the hands of people who do not understand seismic retrofit theory and practice as they should. So conceptually it's great, but as you can see, it's got a lot of problems with the way the plywood's nailed. It's got a lot of problems with the values that are given to the various types of hardware, no consideration of species of wood, all sorts of problems, but they'd be easy to fix. It just needs, a committee needs to get together for, I don't know, 5 or 6 meetings or something to fix it. So anyway, if you have any concern about public safety and this use of Standard Plan A and the fact that literally millions of dollars are being spent with this every year, probably more than that, if you have any concern, talk to somebody that might be able to help. I've talked to everybody and nobody's been able to help. So anyway, if this video was helpful to you, please let me know. Go to the comment part of YouTube and shoot me a comment. And so anyway, hope to see you at the next video.